So why are we doing these slope fields? Well, in reality, when you're doing like physics, there are a lot of things that we want to figure out, like how they're going to change, but we only know the derivative, or the second derivative. For example, like gravity, here's the Earth, we know that the second derivative, dx dt squared, or the acceleration, is pointed this direction everywhere. And the idea of a slope field is we are telling people which direction things will be accelerated. And then, kind of like what we did in the last video, is we would like place an object here and then we'd be able to trace out a path, and the path should always follow the field. Okay, so in this case, what we're trying to do is kind of describe particular cases and actually get the equation of their movement based on the fields here. So again, if you have the Earth and you have acceleration or velocity derivative going down, we know exactly where an object is going to head. If I put an object here, it's going to go down to the ground. And I could write an equation for this path. This point that I keep placing in the field is called the initial condition. So let's do an example here. Here we have a more complicated slope field. You could graph kind of what it would look like by hand, or you could go to Desmos and take a look at it here. Now, if I was to place like a point here, the slope, and follow the slope, the particle would pass through this field kind of like that. If I place a point right here, the particle would kind of curve along the path like that. So imagine this is kind of like gravity guiding things along. Alright, so our job is to figure out an equation for what the path would actually be. So this is what's called solving a differential equation. I know the derivative. I need to find the position. So these are called separable differential equations because what I need to do first is get x and y separate. So what I'm going to do is multiply y over and dx over. So if I multiply by y on both sides, I get y dy over here. If I multiply by dx on both sides, the dx's will cancel, and I'll have x dx. Okay? Now, why are we separating the variables in this way? The reason is that we want to be able to then move up a level. And if this is the derivative, we want to move up to the position, meaning we're going to have to integrate. But it follows the rule of algebra, the golden rule, that whatever you do on one side, you must do to the other side. So we're going to integrate both sides. What's the integral of y? That is 1/2 y squared. And what is the integral on the right side? That's 1/2 x squared. Now we have to include a plus c because we're integrating. So why don't we include a c on the other side? Well, the c over here would not really matter because remember that there's only one c when you move up. And so I can kind of consider all constants to be the same here. So what in the world am I talking about? Let's say I had an equation plus 2 equals an equation plus 4. So this is like one of my c's and this is my other c. Now, because I have a c on both sides, does it really matter if I write it this way or subtract 2 over and just consider 1 here? So it's the same thing over here. If I had a c over here, I could actually subtract it over and I wouldn't have to worry about it because they would just be combined. Alright, well, if that doesn't make sense to you, that's okay actually. Just remember that we do need a plus c. The good news is we only need it on one side. So here's the other thing. We need to actually get this to be a function. What that means is I want to get y alone. So I'm going to multiply by 2 on both sides. On the left side, that would cancel with the 1/2. 2 times 1/2 x squared will be just x squared. And so here's the other funny thing about constants. If I take a number and multiply it by 2, it's just going to be another number. So we can just call it a c. So originally, if we were to work this equation out and we got a 5 here, once I times by 2 on both sides, it's going to be a 10 here. It's still a constant. So another good thing about this is that if you have a constant and you do anything to a constant, like multiply, divide, add, or subtract, it actually just remains a constant. Okay, so I have to get y alone. I'm going to square root both sides. Alright, so that was a lot of work. Let me run through this again. I got my y and my x together on both sides, separated. So I got my y's with my y's, my x's with my x's. After I did that, I integrated both sides. I only have to put a plus c on one side, and then I want to get y alone. This is the equation for my line. So this c here represents some starting value. So for example, when you have something that you're dropping from like a tower, often this c would represent like your starting height. So it depends on the context. Let's go back to Desmos here, and let's just write y equals the square root of x squared, and let's just throw a c in here, like plus 2. Now what that means is that, well, I'm starting here, and this equation, you can see it follows the grid lines. Now what happens if I change my c here? So if I decide instead to do like plus 5, you'll see it just got shifted up a little bit. What happens if I do like a minus 3? Okay, now you notice instead of being up here, we're over here, and it's kind of following the grid lines in this direction now. So that's the second part of this. Yes, it was a lot of work to get the actual equation for the differential equation, but they're also going to give you something like this: y equals 0. Sorry, not y equals. Y of 3 equals 0. So what you should think about this is that this is an initial point. That is, if we put in 3, we get 0 out, and on my equation that means that I have a point over at 3, 0. So you can kind of see that the graph would kind of go up. It'd be very similar to this one, it'd just be over starting at 3. So what does that mean? That means if I plug in a 3, I should get a 0 out. So in this equation, 0 is y. I put 3 in here, I get 9 plus c. So I'm taking this 0.30, which is what that is saying, and I'm plugging it into there. So I solve this. I square both sides. I subtract 9 over. And so this is a particular equation that we wanted to pass through 3, 0. Okay? So this would describe any equation. What I have now here is a special one of those equations that I know will pass through 3, 0. Let's go back here. So I'm going to get rid of this one. I'm going to subtract 9. And now let's double check. Yes, it starts at 3, 0. And it follows the curve. So in your homework, you're going to have to do a few things. First of all, you're going to have to separate, integrate, get y alone. That's your differential equation solution. That represents all the possible curves that could flow through this slope field. But then they're going to give you a point like 3, 0, and they're going to want you to test it out and get the c, and then if you were to graph it, you would see it would go through 3, 0 following the slope field. So allow me to give you an example to actually try out. You're going to try out dy dx equals x squared y. Okay, so you should pause the video now and just try to get the solution to the differential equation. And by the way, to make things easier, you should probably also get the slope field just to kind of visualize what will happen. Okay, so I just put it up on the slope field here. It's kind of a crazy slope field here, but we're going to see kind of curves coming this way, going up, flattening out, going up again, and shooting up. Okay, now off to separating. So in this case, we want y's to be on this side. I'm going to divide by y on both sides. The way to think about that might be that you could multiply by 1 over y. Because if I multiply this whole thing by 1 over y and 1 over y times y cancels. Alright, and then I'm going to multiply by dx on both sides. So just like last time, we have our x's and our y's separated. Alright, the next step then is, once it's separated, is to integrate both sides. The integral of 1 over y is ln of y, and the integral of this would be 1/3 x cubed, and we only need one c value. Now this in itself is an okay equation, but we want to get y alone, and so if you remember from logs, to solve this we have to do like e to the power of this and e to the power of this on both sides. What ends up happening is that this will turn out e to the ln of something is just y, but on the right side we have e to the 1/3 x cubed plus c. All of that is up in the exponent. Now there are some ways to simplify it, but really let's just stop there and say this is the answer. Now the second part would be they will give you an initial value, say of 0, 2. So once you have this, how do you find the c value using that point? You should pause the video and give that a try. Okay, so for example, or what we would do is we would write it out with x and y substituted. So x's, and I wrote y, but really y should be 2. Now this comes out to be 2 equals e to the 0 plus c. So really this is e to the c equals 2. And again, you're solving with exponentials and logs. So if you natural log both sides, you would get c equals ln of 2. Now that means in the particular case where we want this curve to go through 0, 2, we would write 1/3 x cubed plus the ln of 2. And remember, the ln of 2 is a number. Off the top of my head, I can't remember what it is, but it's like, I believe it's 0.7 or whatever. It's an actual number. So if you were to actually go to a calculator and figure that out, that's okay too. Now let's go to the slope field. This crazy slope field should have a solution of y equals e to the power of 1/3 x cubed plus c. Oh, and before we even do the plus c, if c is 0, you see that this crazy graph follows the slope field perfectly. So let's do the plus c. The plus c is the ln, you can type in ln, of 2. Oh, except that should be upstairs, so I need to put this back in here. Plus, oops. Okay, there we go. We just had to have parentheses around that. So it is e to the stuff up there plus ln of 2. And if you check, it is going through 0, 2. So the curve is kind of jumping up, following the slope field, flattening out, then jumping up like the slope field said it should.